In 5.5, instead of talking about solving systems of equations, now we're talking about solving systems of inequalities. Remember, in inequality, I'm going to be talking about greater than, less than, greater than, equal to, less than, or equal to. The graph that represents the solutions of a linear equation is going to be a straight line because it's every point on that line satisfies that one equation. The graph that represents the solutions of a quadratic equation is going to be a parabola because any point on the parabola is a solution to that quadratic equation. The graph that represents the solutions of a linear inequality, though, remember an inequality is going to be less than, greater than, less than or equal to, greater than or equal to. Instead of the line representing the solutions to the inequality, the solution set is the half plane. Because I'm talking about what is less than this, or what is less than or equal to this. So anything from that line less than, or from that line greater than. Graphing an inequality is really not hard. You graph a boundary line and then you check a point so you know where to shade. That's all you're doing. You graph a line, you check a point. Now, your line is not necessarily a line. It could be a parabola, it could be a circle, it could be a cubic function, but you graph whatever the equation represents. And then you determine which side of that you're going to shade by checking a test point. All right, when I'm graphing my inequality, I first rewrite the inequality as an equation, and I graph it as a boundary line. If the inequality is just greater than or less than, then the line is dashed or dotted. It's not solid. If the inequality is greater than equal to or less than equal to, if it can be equal to the line, then the line is a solid line. So that matters. That's the first thing that you have to watch for. The second thing is that you're going to check a test point, and the only qualification for your test point is that your test point is not on that line you just graphed or on that parabola that you just graphed. It has to be anywhere else on the coordinate plane, just not on that boundary you graphed. You're going to take those values for that test point you picked, x and y, and you're going to plug it into the inequality that you were given. Now, the origin is a nice, easy test point unless the origin is on your graph. If it's on the line or the parabola or the cubic function that you graphed, you can't use the origin. So you can't use just 0, 0. You have to pick something else, anything else. If you plug those values for x and y into your original inequality and you get out a true statement, then you're going to shade that side of the line. Whatever side the test point is on, you shade that side with the test point. What if your statement is false, though? What if you plug in your values and you get a statement that is not true? Well, you don't have to test another point. If it's not that side, it's the other side. The side that doesn't include your test point. So you only ever have to test one point. You either found the side you need to shade, or you know you need to shade the other side. Okay, we're going to practice this. First things first, we're going to graph the inequality y is greater than x. Y is greater than x. Our boundary line, I rewrite that as an equation instead of an inequality. And the equation would be y is equal to x. Notice my inequality symbol. So when I graph my boundary line, it is going to be dashed or dotted. It is not going to be solid. Now that equation y equals x, we should be familiar with because we've used it to reflect an equation in its inverse. It's a linear function with a slope of +1 that goes through the origin. So my line y equals x is just this line with a slope of +1 that goes through the origin. And I'm going to graph it as a dotted line because it's not or equal to, it's just greater than. Then I check a test point so that I know which side of that line to shade. My test point can be any point anywhere in my coordinate plane except a point that's on this line. Cannot use the origin this time because the origin is on that dotted boundary line. So I'm going to pick some other point. I could pick a point here or here or here or here or here or here. I'm going to choose to test the point 3, 0 just because. It's just a random point I picked, I promise. So let's plug that test point, 3, 0, point not on my boundary, into my original inequality. My inequality is y greater than x. Here, 3 is x and 0 is y. And so what I get is 0 is greater than 3, which is false. That is not a true statement. What that means for me is that this test point is not part of the solution set. If this test point is not part of the solution set, that means this side is not the solution set, which means the other side is the solution set. And I'm going to shade that other side of the line. This half plane on this side of my boundary line, that's the solution set for this inequality, y greater than x. All right, let's do another. Now notice we're not doing systems yet. We're just doing individual inequality statements. We're going to get to systems. Graph the inequality 8x plus 3y greater than or equal to 24. Greater than or equal to, so immediately I know that my boundary line is going to be solid because it's or equal to. I need to decide how I'm going to graph this line. I have some choices. I can choose to find the intercepts by plugging in 0 for x and then 0 for y and finding those 2 points. Or I could rewrite my line as in slope-intercept form, solve for y. That's the way I like to do it. So I'm going to solve this equation for y. I'm going to move the x over. So that would be 3y equals negative 8x plus 24. Remember, I wrote it as an equation because I need to graph it as a line. And then I divide everything by 3. So I get y equals negative 8/3 x plus, well, 24 divided by 3 is 8. So this is the equation for my boundary line. And I know that I want a solid line. My intercept is 8. So 1, 2, 3, 4, 5, 6, 7, 8 right there. And my slope is a negative 8/3. So I'm going to go down 8 and over 3 to get the next point. And then I need to graph that as a solid line. I need to graph that as a solid line. So I'm going to pull out my little handy-dandy Post-it pad here to use as a straight edge and graph it as a solid line. There's my boundary line. It's solid because of my inequality means or equal to, so it can include the line. The next step is to check a test point so that I know where to shade. Well, my test point this time can be the origin because the origin is not on the line, and this is why I like to test the origin. Because when I plug in those values for the origin, I'm plugging in 0, 0, and that usually greatly simplifies things. So I'm going to test the origin 0, 0. It's not on my boundary line. And I plug it into this equation, inequality, excuse me. I plug it into my original inequality. So I have 8 times 0 plus 3 times 0 should be greater than or equal to 24. Well, 0 plus 0 is 0, and 0 is not greater than or equal to 24. So when I test my point, it's false again, which means this side is not the solution set. The other side is the side that I need to shade as the solution set for this inequality. So that is the graph now. So everything on this side of the line is a solution to my inequality. Next inequality statement is y less than or equal to 4. Because it's or equal to, I'm going to have a solid boundary line at y equals 4. Well, y equals 4 is a pretty simple line to draw. Is it a horizontal line or a vertical line? Well, if y is equal to 4, 1, 2, 3, 4, y is equal to 4 all the way across, right? So y equals 4 is a horizontal line at 4, and it's solid because my inequality statement is or equal to. Which means that, again, I get to pick, I can use the test point as the origin if I want to because it doesn't go through my boundary line. So I can test the point 0, 0 into this equation, inequality. I keep misstating that, I apologize. Into the inequality, y is less than or equal to 4. Well, at the origin, y is 0. 0 is less than or equal to 4. That statement is true. That means that the origin is part of my solution set. So I'm going to shade everything down here. Now, that was expected because I'm looking at everything less than or equal to this y value of 4. Sometimes you can predict it like that. Sometimes you can't because of the way negatives fall out and the way your equation is set. So do not assume that you know which side to shade. Take a second, check a test point to verify your supposition before you shade. Okay, now we're going to move from solving an individual inequality to solving a system of inequalities. The solution to a system of inequalities is the intersection of the solutions of the individual graphs. So I need to think about, what is my solution set? Where am I going to shade for this equation? Where am I going to shade for this equation? And the solution to the system is where those two overlap. Now we're going to take advantage of colors coding to help us get that shading right. On my math lab, you are just going to shade the solution that is the solution to the system, not the solutions to the individual inequalities. So again, color coding. We're going to start with color coding. My first inequality is going to be a solid line at x plus y less than or equal to 4. So my boundary line for the first equation, first inequality, is going to be solid. The boundary line, if I rewrite this as an equation and solve for y, my boundary line occurs at y equals negative x plus 4. Y equals negative x plus 4. So when I come to graph this boundary line, y equals negative x plus 4, I'm going to draw a solid line. It goes through the intercept 4, 1, 2, 3, 4, and I have a slope of negative 1. So I go down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. So if I go down 4, I'm going to go over 4. And that's what this boundary line looks like. Solid line right there. Now I want to go ahead and shade this line. I'm going to check a test point. I'm going to use the origin, 0, 0. Plug that into my inequality statement. 0 plus 0 should be less than or equal to 4, and that is a true statement. 0 is less than or equal to 4. That's true. So that means this origin is included on the shading of this boundary line. So for this first inequality, I'm shading everything over here. All right. Now I'm going to change colors so we can do the other inequality. My other inequality is x minus y is just less than 4. So this is going to be a dashed or a dotted line. And when I write it as a boundary equation, I have negative y is equal to negative x plus 4, which means y is equal to x minus 4, which gives me a y-intercept at negative 4, 1, 2, 3, 4, and a slope of positive 1. So I'm going to go through this point again, but my line has a positive slope, and I need to remember that it is a dotted or a dashed line. So when I sketch my line in, I need to make sure it is a dashed line because it's not or equal to. It's just less than or greater than. Oh, less than in this case. Now I'm going to check a test point for this boundary, and I'm going to go ahead and check 0, 0 because the origin is also not on this boundary line. If I plug in 0, 0 to this inequality, I get 0 minus 0 is less than 4, and that is also true. So that means I'm going to shade this side of my red line. And can you see where those shadings overlap? The solution set to the system is this quadrant where they are both shaded. That's the solution to the system. So in my math lab, you're just shading this quadrant. You're graphing your boundary lines. One is solid, one is dashed or dotted, and then you are choosing to shade this quadrant. Let's do another system. Our first inequality, y greater than 2x minus 3. And then we're going to change colors to do the other one. Y greater than 2x minus 3. My boundary line is going to be dashed or dotted, and it's going to be drawn at y equals 2x minus 3. Well, it's already in slope-intercept form for me, so that's nice. So my intercept is a negative 3, and my slope is a positive 2. So I go up 2 over 1, up 2 over 1. There's where my line needs to go. Let me see if I can find a little bit smaller straight edge. There we go. And this line is dashed. Try to remember which one's solid, which ones are dashed. This line is a dashed or a dotted line. So there is that boundary. And then I need to check a test point for this boundary line. I can use the origin because it's not on my boundary line. So I can test the point 0, 0 into that inequality. 0 greater than 2 times 0 minus 3. Well, that gives me 0 is greater than negative 3, and that is a true statement. So this is I include that point in this side that I shade for this boundary. Let's go back and let's do the other boundary line and test a point for it. This time, again, I have a dashed line because it's not or equal to at y equals negative x plus 6. My y-intercept is 6. And I'm going down 1, so slope of negative 1, down 1 over 1. That means I go down 6 over 6. 1, 2, 3, 4, 5, 6. And I need another dashed or dotted line connecting those points. It only takes 2 points to graph a line. And I need to know which side of that line to shade. I can test the origin because the origin is not on this boundary line. So if I plug in 0, 0 for x and y, I get 0 less than negative 0 plus 6. Well, negative 0 doesn't make any sense. That's just 0, which means 0 is less than 6, which is a true statement. So I'm going to shade this side of my green line. And I can see that again, I have this quadrant where that cross-hatching occurs that is the solution set to that system of inequalities. Okay, we're going to do one more system together, and then I have a written assignment set up for you guys that will be posted. We're going to use the same process whenever I have a nonlinear system of inequalities. I graph boundaries, I test points, and I shade. Let's start with our first inequality, and this is not a linear inequality, it's a quadratic inequality, which means when I sketch my graph, I'm going to be sketching the graph of a parabola. My parabola is going to be solid, not dotted or dashed, and it's going to be drawn at y equals x squared minus 4. Now let's think about transformations of functions. This is a parabola that has been shifted down 4. So instead of the vertex being at the origin, 1, 2, 3, 4, the vertex is down here. Now I'm not going to be super concerned about the x-intercepts right this second. I'm just going to sketch a parabola. I know it opens up. I think I got my x-intercepts pretty close because 2 squared minus 4 is 0, so I'm going to intercept at 2 and negative 2. Yeah, that's better. Okay. So there's my parabola, test point. I still need to know where I'm going to shade. Do I shade inside the parabola or do I shade outside the parabola? I can test the origin because it's not on my boundaries. So if I plug in 0, 0, I would have 0 greater than or equal to 0 squared minus 4, which 0 is greater than or equal to negative 4. That is a true statement. So I shade inside the parabola for this first inequality symbol. Now we're going to look at the other inequality symbol. It is linear because I have x and y, nothing is squared or cubed or anything else. So it's going to be linear, and it's also going to be drawn as a solid boundary. If I rewrite this in equation form and solve for y, I would have negative y equals negative x plus 2, and then I divide everything by negative 1 to get y equals x minus 2 as my boundary line I need to draw. This boundary line has a y-intercept at negative 2 and a slope of positive 1. So this boundary line is going to be a solid line right there. And I need to know where to shade. I can use the origin as a test point again. So if I test the point 0, 0, plug it in there, I have 0 minus 0 greater than or equal to 2. 0 greater than or equal to 2, that is false, which means I don't shade above this line. I shade below this line, And when I shade below this line, I see that the place where the two inequalities intersect is this oddly shaped little piece at the bottom of my parabola. That shaded area in purple is the solution set for this system of inequalities.